Right. That was my two interpretations also. So it's a question of repeats, right, versus uniqueness. So we're picking eight-letter words from 26 letters. So 26 letters, 8. So when someone says pick 8 of these things, it's kind of ambiguous if you're allowed to pick the same thing more than once, right? If we know we're forming words, we'd usually say, yeah, we can go ahead and use 2 S's if we want. But if, you're at a salad bar and you can pick any 3 items, you can pick the same item more than once. But sometimes when we say pick 3 of these things, you pick it and it's done, right? So I think that's the ambiguity they're talking about. So if you're allowed to repeat, yeah, it is. So if you're allowed to do repeats, how many ways can you form an 8-letter word out of 26? Right, so 26, 26 to the 8th. Right, so what rule do you use to get that?
If you can keep using any letter after you pick one for the first, that it's an independent event each time.
Mm-hmm.
You keep using 26 for every selection.
Right, so it's a product rule where each task is to pick a letter, and task I does not influence task I plus 1's choices. It doesn't restrict. So you have 26 ways to do each task. Multiply 26 8 times, that's what you get. But without repeats, then you're picking 8 things from 26, and you're paying attention to the order. Because if you rearrange the letters, then you have a different word. If you just wanted to create a pile of 8 letters, and you didn't care about the order, right, that's a combination. So it's a permutation divided by the number of ways that you could rearrange those 8 letters. All right, so 2.1, 3, 5, and 15. So certain shirt comes in 4 sizes and 6 colors. And 3 pockets. And so how many different shirts could you order? And it's a straight product rule, right? Your task is pick a size, pick a color, and then pick what kind of pocket you want.
Good question. I think the pocket choice is only available for one of the colors.
Oh, is it?
Yeah.
No, it's the pictures that are only available for one color.
Yes.
Oh, okay.
A dragon, an alligator, or no emblem on the pocket. Yeah, so your pocket can be 3 different ways, plain, with a dragon, or with an alligator.
But there's something that was specific to one color. I thought.
Really?
Yeah. It may not have been the pocket.
A certain shirt comes in 4 sizes and 6 colors. One also has the choice of a dragon, an alligator, or no emblem on the pocket.
So I interpreted it as one of the shirts. That may have been one.
Oh, one shirt also has the choice.
That may have also
That's another
been
ambiguity.
Yeah.
So I meant one as in you have the choice of. But that's an interesting ambiguity, right? It's this pesky human language. So if it means that a person has the choice also of this, right, then it's just a straight product rule, 4 times 6 times 3. If it's saying that if one color had a choice of pockets, right, then the problem gets a little more complex. So you have 4 sizes, and you have 5 colors. And no pocket choice, presumably, so that's 20 ways. Or you can pick 4 sizes one color, and 3 pocket choices, which is 12. So it's a combination of product and sum rules, so then you have 32 options. If you interpreted that one to mean one shirt or one color. That's interesting, I never noticed that. All right, question 5, wishes to have a picture taken of its 6 officers. They will be in 2 rows of 3 people. How many different ways can they be arranged? So 2 rows of 3 people, how many ways can you arrange 6 people? And the fact that it's 2 rows doesn't really make a difference, right? We can just number these position 1, 2, 3, 4, 5, 6. And it's no different from if we had 6 people standing side by side or standing one in front of the other. It's still just a simple ordering question. How many ways can we arrange 6 people? So it's really just P 6 comma 6, or it's a straight product rule, 6 times 5 times 4 times 3 times 2 times 1. Either way, it's 6 factorial, so 720. And then 215, you have a choice of fish, lamb, or beef, peas or carrots for a vegetable, and pie, cake, or ice cream for dessert. This is a good restaurant. If you must order one item from each category, how many dinners are possible? And that's just another product rule, right? So number of meals, number of vegetables, number of desserts, multiply them.
So if not ordering the thing was option, would that just increase it from like 3 to 4?
Yeah, that gives you another choice, basically. Yep, good.
A good idea for a food truck. Just simple choices. But
Yeah.
15 different meals.
Yep. All right, and then 2.2, 1, 3, and 7. So raffle has 3 different prizes, and there's 1,000 raffle tickets sold. How many different ways can the prizes be distributed? So there are 3 different prizes. Okay, the word different is key here. So how many tickets? 1,000 tickets, and you're trying to choose 3 of those 1,000 tickets to be winners, and the order presumably matters because you're going to pick who gets the first prize, the second prize, and the third prize. So that's just P 1,000 comma 3, which if you multiply it out is 1,000 times 999 times 998. Okay, 8-letter words we did question 3. Question 7 we talked about the other day. So if you can fill the positions any way that you want, it's number of 5 permutations from 15. Right, because the positions presumably are all different. If you have one of 2 particular people who must be the center, then you can break this into a succession of tasks. First task, pick the center. Second task, pick the remaining 4 people. So the center can be chosen in 2 ways. And then the remaining 4 people will be 14 people left trying to fill 4 positions. And you multiply those because it's a succession of tasks. Two, 3, 7, and 2, 4. 1, 3, 5, and 13. So 2-3, question 7, a survey of 90 people. "47 of them swim, 47 of them play tennis, 42 of them swim, and 17 do both. And how many participated in neither?" So who did this one? Who wants to explain it?
Well, the way I did it was I took the number of people in the first group, this one, added it with the number of people in the second group who did tennis.
Okay.
The order doesn't matter there. And then I subtracted the number of people who did both, so subtract the percentage.
And that gives you,
And that gives you how many people are participating in an activity.
okay, cool. So principle of inclusion, exclusion. The number of elements in the union is the sum of the elements in each set minus the number of elements in the intersection, the overlap. So 47 plus 42 minus 17 is 72. And we want to know how many did neither. So we're looking for the complement of that. So 90 minus 72 is 18. So that's the number of people in the complement. Good. All right, 2.4, question 1. You want 3 faculty members and 4 students. And you've got a total of 10 faculty and 25 students who have been nominated, and we're trying to choose 3 faculty and 4 students. And the order does not matter, right? There's no distinction made between who the members of the committee are. So 2 tasks, right? Choose 3 faculty members and then choose 4 students. So we're going to use the product rule. So the number of ways that we can choose 3 faculty out of 10 is 10 choose 3. And the number of ways to choose 4 students out of 25 is 25 choose 4, and those get multiplied. And this is 10 times 9 times 8 over 2 times 3. And this is 25 times 24 times 23 times 22 over 4 factorial 24. And you multiply that out and you get something like this. I don't remember exactly, but it comes out on a calculator.
In the 25 choose 4,
Mm-hmm.
doesn't the denominator also have 21?
Yes, that's why the top only went down to 22. So I skipped steps here. Right, so then I just canceled those. But yeah, so remember the general formula.
So when you say P and C, what exactly are you saying?
P is the number of R permutations of n objects. C is the number of R combinations of n objects. So the number of ordered arrangements of R objects from a set of n, the number of unordered arrangements of R objects from a set of n. Right, so the order, non-order makes the difference between a permutation and a combination. And the reason this is unordered is because we're dividing out an extra term here, which is the number of ways those R objects could be rearranged. All right, power set-ish question. set of 10 elements, and we want to know how many subsets contain exactly 7 elements. So we're picking 7 elements from a set of 10. Does the order matter? All right, we're forming a subset. The elements of a subset, the order is irrelevant. So it's the number of unordered ways we can pick 7 things from a set of 10. Right, remember that's just a shorthand for 10 choose 7. All right, and then question 5, binomial expansion, 2x minus 3y to the 4th. And this is just playing around with that theorem that we saw where the coefficients of a binomial expansion are the number of combinations.
For the previous one, it says at least 7, so.
Oh, does it say at least 7?
It does.
Ah, okay, so we're not done.
7 plus 8 plus 8.
Yeah, so plus 10, 8. Thank you. All right, binomial expansion, it's basically 2x to the 4th, and this is a coefficient of 4, 4, which is just 1, plus coefficient 4, 3, 2x cubed minus 3y to the 1st, plus 4, 2, 2x squared minus 3y squared, and so on. And then you can expand what those come out to on the right. All right, and then the fun geometry one. I think this is a really cool problem. So question 13, 10 points on a plane, no 3 of them are on the same line. So P1, P2. Hopefully none of those are collinear. So part A, how many lines are determined by the points? Combination 10, 2, right? It doesn't matter what order we pick 2 points in, but if we pick 2 points, that determines a line. And if we pick P1, P3, it's the same line as P3, P1. So the question is, how many unordered ways can we pick 2 points out of 10? So that's just 10 choose 2. And then how many triangles are determined by the points? That's just 10, 3. Which I think is kind of cool. Yeah, I'll bet. And the collinear part's important because that tells us any 3 points will give us a triangle. If we had 3 points that were in the same line, then those wouldn't actually form a triangle, legally speaking.
So I did this kind of wrong.
Okay,
I'm sure I got the
different.
answer. But because I noticed how you couldn't have every point would be able to connect to every other point. So I said it was n plus n minus 1 plus n minus 2 all the way to 0, right? Because when you get to the first one, there'll be n new lines created. The second one will be n minus 1 because you already counted 1.
Okay.
Now, I think I remember you saying something about this sequence of which is the sum of I. Is that the same thing as this n factorial?
It shouldn't be, but what you're describing sounds plausible so far, so let's think about this some more. So pick P1. There's 9 lines that contain P1. If we pick P2, there's 8 new lines that contain P2.
Yeah.
Yeah, so I'm believing this.
But didn't you say something about, like, that function when you introduced us to the C stuff? 'Cause I was trying to get it to look nice. And
Yeah.
it ended up saying the sum of I.
So this is a very cool observation, right? So it's 9 plus 8 plus 7, right?
Yeah.
And this is 10 times 9 over 2, which is 5 times 9, which is 45. And that is what you get when you do this, right? Because this will be 9 times 9 plus 1 over 2. So you have discovered a theorem which looks like that. Number of ways to choose 2 things out of n looks like n times n minus 1 over 2. And in fact, that's exactly right, because how many ways can you choose n things? Well, choose 2 things out of a set of n. Well, the first thing you can choose n ways. The second thing you can choose n minus 1 ways. And if we don't care about the order, we have 2 ways we could have picked those, a, b, or b, a, so we divide by 2. And that gives us the same thing. And this is 1 plus 2 plus up to n minus 1. So that's pretty cool. We'll call it Arbuckle's there.
Because I was, when we were thinking of probability, I ran into a similar function. Well, whatever your first example was, you said it was n squared. It was like, it's not n squared, it's n squared minus something.
Mm-hmm.
And I figured n squared minus n plus 1 plus n plus 2. I was trying to figure out the
Yeah.
for that. Good to know that there is a thing to write that.
Yeah. So we observed in Pascal's triangle that this diagonal was the sum of consecutive integers, right? And if you think of this as the 6th row, this is 6, 2, this is 5, 2, this is 4, 2, and so on. So there's your property inside Pascal's triangle. That's why the sum of this diagonal is always the triangle numbers. So that's pretty cool.
And also, for B, I'm a little unrelated. I didn't account for, like, I didn't know how to do that. Your repetitions. I just said n over n minus 3 factorial, n factorial over n minus 3 factorial, and that would be just that wouldn't be right, would it?
No, you want n factorial over. No, that's.
Well, because it would be n minus
Yeah, that's
3
right.
factorial times 3 factorial, right?
Yeah. So the permutations would be. Right, that's the number of permutations. And then if you want to count triangle ABC is the same as ACB is the same as BCA, etc., multiply by the number of ways you can arrange those 3 objects. Right, and then this is the number of combinations. And I think you could do what you did with multiplying out the cases to find a formula for this diagonal. So this stuff is it's kind of a cool area because, you know, it ties in with probability. Because when you talk about probability, generally what you're talking about is how many ways can you do something? What's the chance of winning the lottery? Well, how many possible lottery numbers are there? Right? And your chance is 1 in whatever that number is. If you buy 50 tickets, your chance is 50 in whatever that number is. If you've got a lead and you know what the first number is going to be and you've got 5 numbers left to pick, right, you can find what the probability is of winning by saying how many different ways can the last 5 numbers come up. So this ties into probability, which itself is a really weird topic to me, right? Because probability never made sense intuitively to me. But it's got factorial, it's got powers of 2, it's got some induction, it's got all kinds of stuff. And I think that makes it an interesting area. All right, so any other questions about that? You usually have some permutation, combination, counting, pigeonhole question on the final. All right, well, back to languages. So we were talking about phrase structure grammars, and we were looking at ways that we could construct a grammar to represent different languages. And we had started doing the synthesis part of that, right? Come up with a language and try to figure out the set of symbols, the set of terminal symbols, the production rules that lead to that particular language. So let's say constructing a grammar. So we've got this 4-tuple vocabulary, terminal symbols, start symbol, and production rules. So we did one grammar yesterday, which was basically 0 to the n, 1 to the n, where n was bigger than or equal to 0. So n zeros followed by n ones. So let's try another one. Suppose our language is equal to any number of zeros followed by any number of ones, where any number might include 0. So 0 or more zeros followed by 0 or more ones, followed by the end of the string. That's what constitutes a word in our language. We did the same number of zeros and ones, right? So we did this one.
You're asking us to create the rule?
Yeah.
So, you could start with, thing, I guess, A. You could say A could turn into 0A or B, and B could turn into 1B.
A can go into 0A or A can go into B.
Oh, I guess it should include 0 too.
I was thinking if we did S as the start, either S could be A or S could be B, but S can also be 0 or 1.
Okay. And then these rules for A and B.
Well, you're gonna have to say A can also go to nothing, and B can go to nothing.
Okay.
That would clean up everything and let it include the none, or the empty word.
All right, so let's see if this works. We got a bunch of rules here. So our start symbol could go to a 0 or a 1. That's fine. It could also go to an A or a B, which could either or both be empty, so that takes care of the empty cases. Our start symbol could also go to a 0A, and that A could go to a 0A, and it could go to a 0A. So it looks like our start could go to a bunch of zeros, followed by an A. And then at some point, that A could go into a B. And our B could be empty, or it could be a 1 followed by an empty or a B, and so on. And eventually it'll end. So I think that's a good production.
You don't
So S can go to A can go to 0, followed by lambda, there's your 0. S can go to B, there's your 1. So are we happy with this? I think it looks pretty good. Say again?
There could be a better way.
There might be a shorter way, but we're not charging. Cool. All right, what if our language consists of 3 zeros or 6 zeros or 9 zeros or 12 zeros or any multiple of 3 number of zeros, but it has to contain at least 3 zeros? So somebody who hasn't contributed already. How about someone on that side of the room? So we know our vocabulary is going to have a 0 and a 1 and a start symbol. Our terminals will be 0, 1. Our start symbol will be S. And we may have some other stuff in our vocabulary.
One of the symbols you could have for in your vocabulary is A.
Okay.
And does lambda count as a symbol?
Lambda is a string.
Okay.
Yeah.
Oh, for production rules, we could have S leads to 0, 0, 0, and
Okay.
you could have A leads to 0, 0, 0, A,
Mm-hmm.
and A leads to lambda.
Nice. So S has to be at least 3 zeros. And what is an A? An A is either empty or it's 3 zeros followed by an A. So an A is either empty or it's 3 zeros followed by a lambda, or 3 zeros followed by 3 zeros followed by a lambda, and so on. So A is actually capturing this idea of some collection of sets of 3 zeros. And by making S go to 3 zeros followed by A, right, we force our language to include at least 3 zeros. If we just did S goes to A could be lambda. So that's forcing n to be bigger than or equal to 1. Nice. All right, how about 1 to the n, 0? So 0 or more 1s followed by exactly 1 0. So it could be 0, 1 0, 1 1 0, 1 1 1 0, and so on. 0 or more 1s followed by a 0.
You could do S goes to lambda B, or actually, instead of lambda, S goes to AB,
Okay.
and then A can be 1 or 0, and then B equals 0, or goes to 0.
All right, so S could be a 0 0, or it could be a 1 0. 0, 0 is not going to work.
That first one. Just A goes to 1, right?
A goes to 1. So S goes to A, B. So this will certainly pick up 1, 0.
Or
A.
1, 1A?
A goes to 1A.
But you also, this one might include just a 0 by itself. So A should also go to lambda.
All right, so it's an A followed by a B. So what is A? It's either empty or it's a 1 followed by an A. So it could be a 1 empty or a 1, 1 empty or a 1, 1, 1 empty. So A is 0 or more 1s, and B is a 0. So I believe that's a great... We don't actually need to have B. We could have just said S goes to A followed by 0. A goes to 1A. A goes to lambda. And that'll work also. So there's your 4 elements of your phrase structure grammar. Cool. Nice work. So a general comment in writing out these lists of transformations. Let's avoid the following. So if we wrote it like this, S goes to A followed by 0, A goes to A followed by 1, or A goes to lambda, that feels like it's capturing the same language, right? Because A could be an A followed by a 1, where A is an A followed by a 1, where A is a lambda, so that would be a lambda followed by 2 1s. That's still a string 1, 1. But this is potentially problematic. So think if you were writing code to analyze a string and try to apply these production rules. To know if we could apply this, we would say, okay, do we have an A? Well, does it start with a 1? And if it does, we would say, okay, it's got a 1. Is the rest of this an A? And we would say, okay, well, if it's going to be an A, it's got to start with a 1. And if it does, we would take off that 1 and say, is the rest of this an A? And eventually, we're going to run out of characters, right? And we're going to say, okay, is it an empty string? Yes, it is. Or we're going to find a 2 or a 5, and we'll say it's not a 1A, it's not empty, okay, it's not an A. But if we have a production rule like this, replace A with A followed by 1, there's no base case in some sense. If we were to write a function that was trying to tell whether our string was an A, the first thing it would say is, okay, well, let's pass this string to our function and see if it's an A. And our function would say, well, I don't know, let's see if this is an A, because it's supposed to start with an A, and it's going to loop forever. And so when you write your production rules, you'd like these rules to be written in a way that lets you actually use up part of the thing that you're trying to parse. Now, there's a whole classification of different kinds of grammars. There's type 2 and there's type 3 and all these different things, and that relates to these. But just kind of from a programming perspective, and we'll probably look at some code for using this stuff later on, this kind of rule makes it harder to write code, right? Whereas this kind of rule is easier.
And that's just the difference between something and one.
Yeah.
Okay.
Basically, if we're saying that an A is something that begins with an A, we've got no real hope of ever getting to the end of our tree, right? If you were to make a parse tree, and we'll do some parse trees on Monday and see how you can apply these things.
Unless you design your parse tree backwards and look for the last character.
Yeah, yeah, right.
The problem with that is if A1 is in the middle, then you have to look for a 1 in the middle, and then
Right, but you might still be able to do that, going in that direction.
What if you have like, say, A goes to A1, or E goes to 1B, but like for different cases, you would switch direction, so you can handle it.
You might be able to do that.
It doesn't sound like a fun time, but.
Yeah, but that might work. All right, cool. So you should be able to do some of your homework at this point. So you can go ahead and get started on that over the weekend. And I will see you right now or in club meeting or on Monday.